Good morning, I'm Lorenzo Olivieri from the Technical University of Madrid, and today I'm going to be talking to you about the retrofitting actions required to convert a real building, the headquarters of the Innovation Technology for Development Center of the Technical University of Madrid, into a net zero energy building. Actually, the objective of the work is to point out the energy-saving measures necessary to convert this simple one-story building into a zero-energy building. So I'll follow this structure with a brief introduction, the explanation of the methodology used, the main results and conclusions. As you probably know, the trend of the building sector is very far from the sustainable development scenario defined by the International Energy Agency, which indicates the global direction that should be followed to meet the three main sustainable development goals related to energy. The fast implementation of high-performance net-zero energy buildings seems to be one of the solutions to fulfill the SDS ambitions. Between the several definitions of zero-energy buildings, the one adopted in this study is that the actual annual consumed energy is less than or equal to the on-site renewable energy generated. Starting from the current situation, this work shows the energy-saving strategies required to cover the annual energy consumptions with the electricity locally generated by a photovoltaic pergola that will be installed on the roof. The methodology is based on the following steps. In the first one, we have performed an exhaustive experimental characterization of the building using an ad hoc design monitoring system that acquires several data such as indoor air temperature, surface temperature, and power consumption every 10 milliseconds and stores them in a monitoring database with more than 3 years of continuous monitoring. Next, we have defined a model of the building, the Unified Tool Leader Calendar, the official tool used in Spain to check the compliance with the technical building code. We have compared, measured, and simulated data in order to validate the model. In the next step, we have estimated the on-site production of a PV system that will be installed on the roof using PVC software. The PV pergola provides a useful multifunctional space on the roof, and it can cover only 1/3 of the roof surface, since the remaining part must be kept free of shadows to be used in other experimentations. At this point, we have defined several energy-saving strategies, such as thermal insulation improvement, perforating metallic double skin optimization, glazing and frame improvement, lighting system efficiency improvement, and heat recovery units efficiency improvements, and for each strategy, a wide range of parameters has been simulated to fully characterize the effects of each of them on the overall energy consumption of the building. Finally, we have combined the best performing solutions, and we have checked the compatibility between them by defining 6 final models that have allowed us to determine the most efficient solution. Well, let's move on to the results now. In the current state, the measured and simulated annual consumptions are very close, being about 130 kWh per square meter. With a difference lower than 3%, the model may be considered validated and can be used to assess the effects of the energy-saving strategies proposed in the next steps. Regarding the distributions of the consumptions, lighting is the most energy-intensive use with about 50%, heating is the second one with 34%, and cooling accounts for about 16%. In the current state, the local generation would cover about 50% of the total energy consumption, staying halfway to be a self-sufficient building on an annual basis. So the question is it possible to reduce the energy consumption by 50% in order to achieve self-sufficiency on an annual basis? The answer is yes, but it requires many actions. as we will see below. Considering that lighting is the most intensive energy use, it was the first one to be optimized. To improve the efficiency of the system, we have considered four main solutions: replacing the T8 fluorescent lamp for LED tubes, introducing an automatic lamp dimming system to make the most of the natural lighting provided by the skylight, using clear colors on both interior surfaces and furniture to maximize the utilization factor, and bring the luminaires closer to the working plane. With these measures, consumption for lighting is reduced by 44%. Next, we focus on the thermal performance of the building, analyze the implementation of an external thermal insulation system. Several insulation thicknesses were simulated to find out a good compromise between performance, economic feasibility, and space issues. We found out that using a thickness of 20 centimeters, energy for heating and cooling is reduced by 10%. Next, we analyze the impact of improving the thermal properties of the glazing surfaces. Four options, including double and triple glazing, were analyzed, find out a maximum energy reduction for HVAC of about, say, 7%. The replacement of the heat recovery units with more efficient one reduced the HVAC consumption by 10%. Finally, removing the metallic perforated double skin in front of the windows produced 5% energy savings. Finally, we combined the best performing solutions in 6 new models. The most efficient combination corresponds to the Model 6, with an energy consumption reduction of about 46%. In particular, the demand for heating is reduced by 56%, mainly thanks to the insulation, high-performing windows, and the use of solar gains in winter. At the same time, the demand for cooling is reduced by 32%, thanks to the improvement of the lighting system and the lower solar factor of the glazing. Moreover, a 44% reduction in lighting consumption is obtained thanks to a significant improvement of the lighting system efficiency. To conclude, this paper shows that reaching net zero energy in this retrofitting project is technically possible, but it's not an easy task at all, since actuations on several building components are required. Thank you very much for your attention.